In this video, we shall look at a challenging problem involving projectile motion. The aim is to show and to demonstrate doesn't matter how involved a given projectile motion is, it can be tackled with efficient setting up of the problem. Now let's look at the problem. A rock is thrown leftward from the edge of the roof, right there, at a height h above the ground. The rock hits the ground 1.6 seconds later at a distance 30 meters from the building. So that's the distance. And at an angle of 58 degrees with the horizontal. What is h? And find the magnitude and angle relative to the horizontal of the velocity at which the rock is thrown. And what can you say about that angle? The first step is to set up the coordinate system like that. So the positive y-axis is going like that, and the positive x-axis is actually going to the left. So that is our choice. Now let's write down the equations. Now this is a kinematic problem essentially, with acceleration equals to that of gravity, and it's going downward. So let's write down kinematics equations along the x direction. We know there is no acceleration along the x direction, so we will begin with the x component of the velocity. We know that the x component of the velocity does not change. If you assume that the object is thrown, let's say, with an initial velocity of u at an angle of, let's call it, theta, then the x component of the velocity at any time is just the x component of the initial velocity. So in this case, you can simply write it as u cosine theta. Now what about the coordinate, the x coordinate? How does that change? It is just vx times time, which is this times time. So it is just u t cosine theta. Remember, in addition to h, we need to figure out this theta and also u, the initial velocity. Of course, we are not told in the question how this rock is thrown, whether it is thrown above the horizontal or whether it was thrown below the horizontal, but that's all right. Let's just make an assumption. When the calculation is done correctly, the real nature of the angle will be apparent. Now let's write down the kinematics equation for the y component, or along the y direction. Now we know there is acceleration along the y direction. That is just gravity. I'm putting a minus sign here because gravity goes like that, opposing the positive direction of the y-axis. The y component of the velocity at any time is obtained from the kinematics equation as the one being written here. Remember this? So u in this case is the y component of the initial velocity, which is u sine theta. Because we know if this is u and that is theta and that is the y direction, then the y component of u is just u sine theta, that one. Acceleration is minus g t. Now let's write down the expression for y coordinate with time. It is just half a t squared plus ut plus the original y coordinate, namely the y coordinate at t equals to 0. So applying that, we have a is again minus g, so minus half g t squared. This one here is u sine theta times t, so ut sine theta, and y naught is the y coordinate at t equals to 0, which is just h. Remember, the y coordinate of that point is h. The x-coordinate is 0. So that is the coordinate of that launch point. So the setup is done. Now let's use the information provided. Now we know the rock hits the ground 1.6 seconds later, and it hits the ground 30 meters from the building. So that means we need to use that equation. When x is 30, t is 1.6 seconds. So 1.6 seconds times u cosine theta. Let's call this equation equation 1. The second information is this 58-degree angle. At the point where it hits the ground, the y component of the velocity is going like that. So that is vy. And the x component of the velocity is going like that. So that is your vx. So this angle here is 58 degrees. Now vy is going down and vx is going along the positive x direction. So the ratio of vx over vy, which is in magnitude equals to tangent of 58, is a negative number. So it's minus tangent 58 degrees. Evaluate it at t equals to 1.6 seconds. Because this 58 degrees with respect to the horizontal occurs at the impact point, and it takes time of 1.6 seconds to impact the ground. Let's substitute vy evaluated at 1.6 seconds and vx from that equation, which is independent of time, and put it in here and get an equation out of it. So vy is u sine theta minus 1.6g divided by u cosine theta equals minus tangent 58. From equation 1, we know u cosine theta is 30 over 1.6. So that enables us to obtain an expression for u sine theta, which will be 30 over 1.6 times minus tangent 58 degrees, and now bring this term to the right, it becomes positive 1.6 gravity. That means your u sine theta equals minus 14.31 meter per second. Now we are ready to find h from this equation. We know what u sine theta is. You can substitute in this equation. When t is 1.6 seconds, y is 0 because the object is here. So let's rewrite that. 0 equals minus half g 1.6 squared plus u sine theta is minus 14.31. Time is 1.6 plus h. And you can solve for the h, which will give you h equals to 35.45 meter. And that's the answer for part A. Now we have to find the magnitude of the initial velocity and also the projection angle. For that, we need this equation and that result. Now we know u cosine theta is 30 over 1.6. We also know u sine theta equals minus 14.31. So this is equation 1 from here, and this is equation 2 from there. By taking 2 over 1, you can calculate tangent theta, and it will be minus 14.31 over 30 over 1.6, or times 1.6 over 30. And solving for theta, you get minus 37.35 degrees. Now comes an important point. Note the angle is minus 37.35 degrees. That means the launch angle is not above the horizontal, but below the horizontal, like that. So that means the rock was thrown in that direction with some angle theta given by this number below the horizontal. What about the magnitude of u? You can use either equation 1 or equation 2 to get u. Let's use equation 1. U equals 30 over 1.6 over cosine theta, which in this case it's minus 37.35 degrees. Doing the calculation, you get 23.6 meter per second for u. And that is the magnitude of the velocity at which the rock is thrown. And together with this angle, we have a complete answer for part B. And that solves the problem. Thank you for watching.